This is a video proof of Stewart's theorem by the Trisectors group at UT Dallas in the spring 2014 semester. Group members include Whitney Almond, Yeelan Park, and Katie Ward. Suppose we have triangle ABC such that side A is opposite to angle A, side B is opposite to angle B, and side C is opposite to angle C. We can draw any line segment from vertex C to a point P on the opposite side, AB, and label this length T. Also, let's label X as line segment AP and Y as line segment PB so that X plus Y equals C. Then, Stewart's theorem is simply a formula based on this diagram. It says that ct squared plus xyc equals xa squared plus yb squared. It's important to note that the line segment T is not necessarily a median, angle bisector, or altitude of triangle ABC. We will discuss a special situation later.
Before we can prove Stewart's formula, we need to review a few other theorems related to triangles. The first one is Pythagorean theorem, which states that for any right triangle, the sum of the squares of the two legs is equal to the length of the hypotenuse squared. In triangle ABC shown here, A and B are the legs and C is the hypotenuse, so we have the familiar formula A squared plus B squared equals C squared. A picture representation of the Pythagorean theorem shows that the sum of the areas of the two squares on the legs of a right triangle equals the area of the square on the hypotenuse. In this case, 3 squared plus 4 squared equals 9 plus 16, which is same as 25, and that equals to 5 squared. Note that this formula is only true for right triangles, which means that one angle measures exactly 90 degrees. There are numerous proofs for the Pythagorean theorem, but here is one that combines geometry and algebra. We start with our given right triangle with sides labeled A for the shorter leg, B for the longer leg, and C as the hypotenuse. Then we construct a large square of the side length A plus B from 4 of these identical right triangles, which also creates an inside square of side length C. Observe that the area of the 4 orange triangles plus the area of the inside white square should equal the area of the large outside square. Using the formula 1/2 base times height for the area of each of the 4 triangles and side square for the area of the squares, we add the areas of all 5 inside pieces together and set their sum equal to the area of the large square containing them. Expanding the binomial a plus b squared and then canceling the like term 2ab from both sides, we find that c squared equals a squared plus b squared, which proves this theorem.
The other theorem that will be crucial for our proof of Stewart's formula is the law of cosines. Given an arbitrary triangle ABC, let A, B, and C denote, as usual, the lengths of the sides BC, AC, and AB respectively. Then the theorem gives the relationship between the sides of the triangle and one of its angles. C squared equals A squared plus B squared minus 2AB cosine C. Similarly, B squared equals A squared plus C squared minus 2AC cosine B. In observing the symmetry of the formulas, A squared equals B squared plus C squared minus 2bc cosine A.
First, we will prove the law of cosines for acute triangles, which are triangles with all 3 angles less than 90 degrees. So let's assume that angle C is less than 90 degrees. Draw altitude AP from vertex A to side BC and label it H. An altitude is the perpendicular segment from a vertex to its opposite side or the extension of the opposite side. Let x equal PC. Then BP equals A minus x. Now, since triangle APC is a right triangle, we know that the cosine of an angle equals its adjacent side divided by the hypotenuse. So, cosine of C equals PC over AC, which equals x over b, which implies that x equals b cosine of C. Next, we can write a system of equations based on the Pythagorean theorem in triangles APC and APB separately. So b squared equals x squared plus h squared, and c squared equals h squared plus a minus x squared. Therefore, h squared equals b squared minus x squared. Plugging the rearranged first equation into the second equation, we have c squared equals b squared minus x squared plus a minus x squared. Then, by expanding the binomial, we have c squared equals b squared minus x squared plus a squared minus 2ax plus x squared. Notice the x squared terms cancel out, leaving us with c squared equals b squared plus a squared minus 2ax. Finally, plugging in the formula we found for x above, we see that c squared equals b squared plus a squared minus 2ab cosine c. Note that a similar proof exists for the other two formulas. For completeness, we will prove the law of cosines for obtuse triangles, although we will not actually need to use it in our proof of Stewart's formula. Assume that angle C is greater than 90 degrees. Extend base BC to meet the altitude h from vertex A at P. Let x equal PC. Observe that angle ACP is equal to 180 degrees minus angle C. So cosine of 180 degrees minus C equals PC over AC, which equals x over b. Now recall the trig identity, cosine of u minus v equals cosine of u times cosine of v plus sine of u times sine of v. So in our case, cosine of 180 degrees minus c equals cosine of 180 degrees times cosine of c plus sine of 180 degrees times sine of c. Since cosine of 180 degrees is -1 and sine of 180 degrees is 0, we have that cosine of 180 degrees minus c equals -1 times cosine of c. Thus, negative cosine of c equals x over b. So x equals -b cosine of c. Applying the Pythagorean theorem on triangle APC and triangle APB individually, the result follows very similarly to the proof for acute triangles on the previous slide. So, from triangle APC, we have b squared equals x squared plus h squared, and from triangle APB, we see that c squared equals h squared plus a plus x squared. Rearranging the first equation, we have h squared equals b squared minus x squared, and plugging this into the second equation results in c squared equals b squared minus x squared plus a plus x squared. Then, expanding the binomial a plus x squared, we get c squared equals b squared minus x squared plus a squared plus 2ax plus x squared. So, canceling out the x squared terms leaves us with c squared equals b squared plus a squared plus 2ax. Finally, plugging in the formula x equals -b cosine of c found above, we have c squared equals b squared plus a squared minus 2ab cosine of c. Note that if angle C equals 90 degrees, then point P coincides with point C, and then cosine of C would equal cosine of 90 degrees, which equals 0, so the law of cosines immediately results in the Pythagorean theorem of a squared plus b squared equals c squared. Finally, we have collected all the information we need to prove Stewart's theorem. His formula is simply an application of the law of cosines. First, apply the law of cosines to triangle ACP and label it equation 1. Then do the same for triangle ABC and label it equation 2. Notice we chose equations that reference the same angle A. Now we can eliminate that term by multiplying equation 1 by c and multiplying equation 2 by x and then subtracting the 2. So now we have ct squared minus xa squared equals cb squared minus xb squared plus cx squared minus xc squared. We can factor out the like terms on the right-hand side to get ct squared minus xa squared equals b squared times c minus x plus xc times x minus c. Notice in the picture on the right that x plus y equals c, so rearranging this we see that c minus x equals y, and therefore x minus c equals negative y. Substituting these into our current equation, we obtain our desired result. Ct squared minus xa squared equals b squared times y plus xc times negative y. Then ct squared minus xa squared equals yb squared minus xyc. And rearranging the terms, we see that ct squared plus xyc equals xa squared plus yb squared. The nice thing about Stewart's theorem is that we don't need any information about the angles of a triangle to apply it. Now that we have proved Stewart's formula, we can apply it to a more interesting situation as promised earlier. Suppose that CP is a median of triangle ABC. A median of a triangle is the line segment joining a vertex to the midpoint of the opposite side. Therefore, x equals y, which equals 1/2 of c. Then using Stewart's formula that we have just proved, we can plug in 1/2 c for x and for y. Then, carrying out the algebra steps, we have ct squared plus 1/4 c cubed equals 1/2 ca squared plus 1/2 cb squared. Canceling out a c from every term, we get t squared plus 1/4 c squared equals 1/2 a squared plus 1/2 b squared. Then, t squared equals 1/2 a squared plus 1/2 b squared minus 1/4 c squared. Taking the square root of both sides, we find that the length of the median is the square root of 1/2 a squared plus 1/2 b squared minus 1/4 c squared. Every triangle has 3 medians, and the formula is very similar for the lengths of the other two. We hope you enjoyed this presentation of Stewart's formula by the trisectors. Whitney Almond, Yeelan Park, and Katie Ward. We would like to acknowledge our professor, Dr. Mohammed Akbar, as well as the Geometry for College Students textbook by I. Martin Isaacs. Thanks for watching.